In this segment, we are going to see how to implement a Boolean function or an expression using a multiplexer. So what happens in such questions is we will be given with a Boolean expression in one of these three formats. I will be explaining all the three formats in a minute. And we have to implement this function using a multiplexer, meaning you have to use multiplexers and some combination of circuits or connections such that when you give an input, your multiplexer gives you the same output which this function would give. Meaning, if for my variables 1, 1, 1, if my function is going to give me a 0, then I have to construct a circuit using a multiplexer such that when I set ABC as 1, my multiplexer also returns 0, and thus correspondingly for all possible combinations of inputs. So, to put it simply, I am given a function and I have to construct a multiplexer which implements that function, meaning for any given combination of inputs, whatever output this function is going to give me, that's the same output my multiplexer circuit is supposed to give me. That's the kind of circuit I am expected to construct. Now we will first start with the inputs and then we will see how a multiplexer is constructed in this context. So there are three formats in which I might be given a function. The first is the normal Boolean expressions, the expressions of Boolean algebra which we are familiar with. The next is the sigma notation, and finally the pi notation. Now this one needs no explanation. From this we can even construct a truth table directly. How? For each of the terms in this expression, the corresponding combinations get a 1 and everything else gets a 0. And what are those combinations? Wherever we have a complement, we denote it by a 0, and where we have a variable, we denote it by a 1. For example, a dash b dash c would be 0, 0, 1. As you can see here, 0, 0, 1 gets a 1. A dash b c would be 0, 1, 1. 0, 1, 1 gets a 1. And a b dash c dash would be 1, 0, 0. 1, 0, 0 is a 1. And for all other combinations, I have marked them with a 0. So when this sort of an expression is given, this is how you derive the truth table. And the other two forms, namely the sigma form and pi form, are just equivalent to this. They are different ways of denoting the same. So when I say sigma 1, 3 and 4, the combinations 1, 3 and 4 get a 1 and everything else get a 0. So if you see 0, 0, 1 gets a 1, and this is the binary equivalent of 1. 0, 1, 1 gets a 1, which is the binary equivalent of 3. 1, 0, 0 gets a 1, it is the binary equivalent of 4. So if something is given in sigma notation, you simply write down all the possible combinations, and the binary equivalence of these numbers, the output for those combinations is a 1. For all other combinations, the output is a 0. And the pi notation is the exact opposite. So pi denotes all those combinations which get a 0. So if you take 0, 0, 0, it gets a 0 here. 0, 1, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1, they all get a 0. So pi notation tells you about those terms which are going to be a 0 in your truth table. So given any one of these terms, or given a question in any of these forms, you should be able to construct the truth table pretty easily. And how many combinations do we take? We take up to the nearest power of 2, meaning if I am given in terms of a, b and c, I know that my question has only 3 variables a, b and c. But if my question is either in the sigma notation or pi notation, how do I identify how many variables are there? You consider the nearest power of 2. So for example, in this question, the nearest greater power of 2 would be 8, and hence 8 is 2 to the power 3, so we take 3 variables. And here you might ask why 4 cannot be taken as such, because see, if I am saying the fourth term is a 1, the equivalent of 4 is a 1, it means I already have at least 5 terms, 0, 1, 2, 3, 4. Meaning I need to go on up, I already have 5 terms. So the number 4 as such is exceeded because we start from a 0. Or in simple terms, what I am saying is, when you have these numbers, either in a sigma notation or a pi notation, look for the nearest greater power of 2, let's say it is n. Then you take 2 power n minus 1 combinations, which is n variables. So here the nearest greater power of 2 must be 2 power 3, which is 8. So I take 3 variables and 8 combinations, and the 8 combinations will be from 0 to 7. So that is how you identify the number of variables if you're given in sigma form or pi form. Now, having identified the number of variables, all we do is we construct this truth table first, and you map the inputs to the outputs. Now, how do we proceed after this? What we do is we generally keep the last variable for our input and all others as our selection lines. We are dealing with a multiplexer here, so we'll have inputs and selection lines. Now, this is not going to be our only input. We are going to use this variable for our input to derive our input, and we'll see how that happens later. But understand that the output is just the output. You're not going to meddle with it right now. The one last variable before the output is always going to be used for your input, and all others will be selection lines. So now how many selection lines do we have here? 2 selection lines. And so from our knowledge about a multiplexer, we know that if it has 2 selection lines, then it's going to have 4 inputs and 1 output. So this is our basic knowledge about a multiplexer. So based on what we derived and what we know of a multiplexer, we know it's going to be a 4x1 multiplexer. Our 2 selection lines, as we just discussed here, will be A and B. 1 output, which I am going to call Y. We have this C variable which we are going to use to find our inputs. We will see how that is done. And we have 4 inputs, I0, I1, I2, I3. Now when people say construct a multiplexer, what they are asking us to do is basically find Boolean expressions for I0, I1, I2 and I3. And we will see how that is done right now. So we start by taking C, which we decided we are going to use for our inputs. We'll have C dash, might come in handy at some time. We have a line for 1 and a line for 0. Now these are the 4 quantities we have at our disposal. Using these, we need to come up with one expression for I0, one expression for I1, one expression for I2 and one expression for I3. So we'll find out how we go about this. So to figure out expressions for the inputs, we come back to our truth table and divide it into groups of 2, starting with 1, 2, 3, 4, 5, 6 and 7, 8. Now, and because we are taking 2 power n combinations, it will always be divisible by 2. You will always get exactly an even number of groups. Now, we discussed that we will be using C to frame our inputs, right? And the input is going to be transformed into something to give us the output. So C is going to be used for input and this is the output. So let's try to find an expression for F in each of these cases in terms of C. And we'll do this for each group of 2. So this is one group, this is one group, 1, 2. So this is one group and this is one group. We have 4 groups. In each group, we'll try to find an expression for F in terms of C. So here it's very obvious, F equals C, F equals C. Here we can see that you have a 0, 1, 1, 0. So F equals C complement and here F equals 0. This is no complicated math, it's simply obvious. If it's the same, you will have F equals C. If it's opposite, you will have F equals C complement. If irrespective of C, if your F is 0 in both cases, you will have F equals 0. And if it's 1 in both cases, you will have F equals 1. So we have found out the 4 cases. The 4 inputs are C, C, C dash and 0. So now these are the expressions for our inputs. So our I0 is going to be a C. I1 is also going to be C. I2 we derived it to be C0 and I3 will be a 0. So this is our multiplexer. So and yeah, here we have a 4x1 MUX. So what does this diagram mean? Essentially it means I have 3 variables A, B, C. I have a 4x1 MUX and I have this function which I am trying to implement. So if I make A and B my selection lines, 2 selection lines, and if the 4 inputs I am going to give my MUX are C, C, C dash and 0, then for every combination of A, B, C, the output that this expression gives and the output that this setup gives will be the same. Meaning, using the circuit, I have implemented this function. This is what we mean by implementing Boolean functions using multiplexers. So, a quick overview of what this entire thing is about. We'll be given a Boolean expression. If it's given directly in terms of the variables, well and good. If not, sigma notation represents those terms for which my output is a 1. Pi notation represents those terms for which the output is a 0. And how do we identify the number of variables that are there if this is not given? You go for the nearest greater power of 2. Once you have the truth table, the last input, the last variable is used to find out the input. The others are my selection lines. Now that I know the number of selection lines, I also know the number of inputs I need. What do we do next? You group your truth table into 2 rows per group, and you try to find an expression for your output in terms of this last variable, which we reserved to use for the inputs. So once you get these expressions, the expressions will always be of the form either C or C dash or 0 or 1. These are the only 4 combinations you can use, assuming your last variable is a C. So once you get those, you just connect those to the corresponding input lines, your circuit is ready.